So by rule number 1 from the definition of k, that part's just 0. So we only have to consider the part 2 case, right? So we're actually going to do integral from 0 to 1 of, what we got? Well, partial a partial t, right? Dt dxj by rule 2 for k, all right? Oh, was that an I? Thank you, yeah. Muchas gracias. All right, I. Now that is an integral that we can do, right? What is it? So by fundamental theory of calculus, we're looking at a of 1 comma x minus a of 0 comma x dxi. Right? The integration is over the first variable, holding the last n variables fixed at x. Right? So they just ride along. But what is that? Why is there a gazebo up there? Like, it's just so, what's the word? Do we have a word for things that are really, really dumb and should be shamed? Dumb? Stupid. Those are good words, but they don't have quite the gravitas that I'm looking for. Inane. I like that. That's intelligent, but wouldn't get me in trouble. Let's stick with that. It's inane. So we're looking at a 1 comma x di minus a of 0 comma x dxi. Can you recognize what we're looking at here relative to my introductory between the red lines over here calculation? Can we? We can rewrite these as pullbacks of what? Yeah, this is the pullback under J1 of omega minus the pullback under J0 of omega. Remember, omega's right here. See that? We're just putting t equals to 1 and t equals to 0. That's all the pullback does. It's like calisthenics on the, I don't know. All right. And hey, so hooray. That's what we wanted, right? That's the result. See, that's exactly what the K-lemma said, yeah?
And that's because d of k of w, or omega is 0.
Oh, did I not do that yet? Oh, but, oh yeah. No, thank you, my bad, notice. K of, my bad, d of k omega is equal to d of 0, which is equal to 0. So k of d omega is equal to k of d omega minus d of k omega in this case, right? Now, why is that 0? Because there is no time part in this omega, right? So by definition, our k just sends it to 0. So there's not much to show there, just by definition. All right, so case 2. Case 2, it's a little bit trickier. I'll do it over here. Case 2, we've got omega equal to, where was I? A of t comma x dt wedge dxj. And so this time d omega is the sum over j of partial a partial xj dxj wedge dt wedge dx big J plus partial a partial t dt wedge dt. Yay, we like that. Dt wedge dt is 0. All right. And let's see here. So d omega, so k of d omega is what? It's actually k of, we can flip those. So we've got minus the sum over j partial a partial xj dt wedge dxj wedge big d big dx big J. And of course that gives us minus the sum over, oh, I seem to have done a sum over k rather than j, but whatever, I'm going to stick with the sum over j because it's more confusing that way. So sum over j of the integral 0 to 1 partial a. Why use two different letters when you have the opportunity to use the same letter twice, just with different capitalization? So partial xj dt, and then dxj wedge dx big J. All right. And I seem to have switched from j to I. It's a midpoint, mid-calculation here. Oops. All right, fine. So that is it. That's it for k of d omega. Now let's turn to the calculation of the differential of k omega. So first I need to, what is k of omega here? K of omega is the integral from 0 to 1 of a of t comma x dt dxj, big J. So then the differential of k of omega is the differential of the integral, where was I? 0 to 1, a of t comma x dt wedged with, of course, dx big J. All right. So there's two pieces there. So we've got partial t of the integral from 0 to t of a of, I need to use a different letter here technically, tau comma x d tau, because I'm differentiating with respect to the variable t. It's I got to pay the piper here somewhere. So that times dt plus the sum over, let's say, j, to keep it confusing, 1 to n of partial a, partial x j of the integral from 0 to 1 of a of t comma x dt dxj wedge dx big J. All right. Then we're assuming here that, well, we're not assuming anything. This is a constant, all right? So that makes that differentiation be 0. And we bring this inside the integral. And that gives us the sum, j equals 1 to n of partial, good grief, the integral from 0 to 1 of partial a partial xj dt wedged with dxj, there's no wedge here, dxj wedged with dx big J. Oh. Oh. Therefore, if we take k of d omega and we add d of k omega, what do we get? 0. But notice that J0 pullback omega is equal to J1 pullback omega is also equal to 0, right? Because this one's got a dt in it, so the pullback with t being constant, these are both 0 because omega's got a dt in it. And the pullback under either the J's maps, J0 or J1, they both pull back differential forms with dt to 0. So this is indeed also equal to, in a kind of silly way, I should wear my glasses, J1 pullback omega minus J0 pullback omega. All right. All right, where was I? At this point, we can put it all together, right? So therefore, thus, K lemma holds. Yeah. Proof done. Why does this help us? So let's see here. Oh, sorry. So let's look, coming back to here, we just need to put this all together. We're almost done. G of J1 of x is equal to x, and G of J0 of x is equal to P, which is to say that G composed with J1 is equal to the identity, and G composed with the J0 map is equal to the constant map P. So if we take a P plus 1 form, if gamma is P plus 1 form on U, then we can pull it back, right? G composed with J1 pullback gamma is equal to the identity pullback gamma, which tells us that J1 pullback G pullback gamma is equal to gamma. And also that G composed with J0 pullback gamma is equal to 0, but that's to say that J0 pullback of G pullback gamma is 0. So if we put these two together into the K lemma, I think I can afford to erase the part between the red lines there. fact, I think we can, at this point, erase the definition of K. I'll try to finish here. So we have so let's see, the K lemma then gives me, so apply K lemma to omega equal to G pullback gamma, okay? And that gives us that K of G pullback gamma, sorry, one more other thing. I keep missing a step. Note, remember the differential commutes with the pullback, so we have the differential of G pullback gamma is also equal to the pullback under G of D gamma, all right? And so that gives me that K of G pullback D gamma plus the differential of K acting on G pullback gamma is all equal to gamma. All right, this is very, very nice. All right. Because if gamma is exact, well, that's what we want. So suppose gamma is closed, all right? Then D gamma is equal to 0, right? But what happens if we take the exterior derivative of the boxed lemma? Oh, I'm an idiot. I'm sorry. Let me. We don't need to take the. I'm a dummy. We don't need to take the exterior derivative of the boxed lemma. We just need to look at the boxed lemma. What's this say then? That means this is 0, right? So the boxed lemma becomes what? The exterior derivative of K G pullback gamma is equal to gamma. But this is, this is the potential form. It's the potential form whose exterior derivative is exactly the form, which this shows gamma is exact, all right? So we earlier today proved that exact implies closed. Now, in this context, we have that closed implies exact. But it's better than that, actually, because if you look at what's going on here, we actually have a prescription of calculation. We have a method to calculate the potential form through the deformation map. Yeah? I won't make you guys watch me write that out. I just want to show you it, and then we'll be done. So. Now it turns out, so I guess the question asked while we're waiting for the camera to work, the lights to work here. What made my two counterexamples to Poincare's, they're not counting, but the counterpoint examples, I guess you could say, what do we want to call them? Cautionary tales. My example 2 and 3. Why were those not, why were those forms closed but not exact? What could we say about those domains? Can't construct J1 and J naught. Well, the J1 and J naught, I guess we could always construct those.
But if you're going to have it to be smooth, you're always going to run into the origin.
But we apparently can't construct the deformation, right? We can't construct the smooth mapping G that interpolates between the J0 and the J1. In other words, the punctured plane and the R3 with the z-axis removed, those are not deformable to a point. Another way to say this is the space is deformable to a point if you can take any loop in the space and contract it to a point. All right? That's to say that deformable to a point is essentially saying what we would call simply connected.
Does it have to be for any point or just for one point?
Well, there just has to exist a point, actually. I mean, we saw in this, it's just there exists a point. But, well, that's a good question.
You can deform it to the origin.
Yeah, I think, I'm not sure what to say about that off the top of my head. Like, certainly if there exists a point, then that's enough. I kind of have a suspicion if there exists one point you can deform to, then you probably can deform to other points, though, is my intuition about that. I will eventually get to it, guys. This is 8:11. It stopped working. All right, so we just got through this. So the next thing is you can a little bit of higher math to talk about here just briefly. The space, so if we look at all the possible K-forms on a space, you know, we can look at Daniel, if you have to go, it's okay. Okay. So the Z, P of U, this is just the set of all closed differential forms on the space U. And then you can look at the subset of those, which are exact. These are the exact forms, all right? Remember, exact implies closed, but there may be closed forms which are not exact, right? So if there are closed forms which are not exact, if you study this quotient vector space, whatever that is, if this is non-trivial, that speaks to the existence of closed forms which are not exact, all right? And it turns out that that defines, well, by definition, that defines what's called the Pth homology group with real coefficients. And the dimension of this is called the Betti number. Essentially, Betti numbers being non-zero for your space is detecting non-trivial topology. The existence of holes in your space, right, basically. And so like my example 2, that angle form on the plane with the point removed says that there's something topologically distinct about the plane with a point removed versus the whole plane, right? It's not simply connected because you're missing that point. Or the R3 with the, the z-axis removed is not topologically the same as the whole of R3. In particular, the Betti number, I think the Betti numbers are both 1 in these cases because like there's just basically, well, anyway. You want to know more about that? Take a class in algebraic topology. I'm just saying that there is a connection between geometry and differential forms in this way. Oopsie. What doesn't exist? Oh, the algebraic topology class? Hey, it existed. It existed once upon a time. I even have some video proof of it. So here is an application of what we just did to the case of, let's see here, I think 3 dimensions is what I did. Suppose you have, a vector field, a smooth conservative vector field on U. Remember that if it's conservative, that means that the curl is 0. And if we're assuming U is deformable to a point, okay, so that's the context in which this all works. D omega F, as we've talked about, is the flux form of the curl, which is 0, which is to say that the work form corresponding to the flux form of a conservative vector field is closed, all right? And as such, I can look at my, my deformation to the point like this. Well, allegedly, we should be able to calculate the potential form for the work form using this business. Now, we might put a minus in there just so that it makes like contact with physics in the usual way, but whatever. So what's the deformation? So I use the origin. the deformation of 3 dimensions to the origin, the mapping, you can just take the point, right, and just shrink it to the origin in like any point you want, shrink it to the origin in time 1. The formula for that is just like g of t comma r equals to tr. So when you put t equals to 1, you've got r. When you put t equals to 0, you got 0. So we can just shrink all of 3-dimensional space to the origin using the formula simply tx, basically, or tr if you want, like I did here. So that's my deformation map. You can actually write it down explicitly. There it is. And clearly that is, wait a minute, I thought g of 0, oh, g of 0 is supposed to be p. The point is the origin. P is the origin here. G of 1r is r, great. So then I have to, well, let's just go on here. When you work it out, come back. Let's see here what I do. At the end of all this, I admit I did more calculation than I needed to. I make some reference to Naruto. But let's see here. G of this is that. So the dg, push forward of partial t is this. The push forward of x is that. The push forward of y is that. And x is this. So if I calculate omega f of dg partial t, I get this, which gives me that. And put it all together, the k acting on the pullback under g of omega f is k of this, which then, oh man, I just barely brushed that stupid thing. It just does that. See, as a Naruto comment here. So my potential is minus the integral of all that jazz, but that is exactly what we get from integrating the force along the path that goes from the origin out to xy. Like this is the path which parameterizes the origin to the point xyz. And so, in short, we're led right back to the usual formula for potential energy for a conservative force. Namely, we take the line integral from the origin to the point you're interested in calculating the potential. That is derived from this larger story of the K-lemma. So what I was telling you before class, Sam, is like I'd like to have another example of how this calculation finds a potential form for something that's much more like higher dimensional. But at the same time, I don't want to do it for a general one. I want to do it for like a specific example. I have worked through this in the next case it's talking about down here, but it's just very much nastier to work. Like there's something for the magnetic field called the vector potential for the magnetic field. Magnetic fields naturally correspond to like a 2 form. So the analog of potential energy for a magnetic field is something like a 1 form. The exterior derivative of 1 form giving you that 2 form, which is the magnetic field. So actually when you study higher level electromagnetism, you find out that there's not a potential for the magnetic field. There's what's called a vector potential. And the relation between the magnetic field and the vector potential is that the magnetic field is the curl of the vector potential. Even if you've had Physics 232, you haven't seen this here. It's not in the elementary course. But anyway, this gives us a general prescription of if you have a closed form on a deformable space, you can go through these things and calculate the potential form, the form whose exterior derivative is your given closed form. There is a procedure for it if you're willing to slog through the mathematics. Or you could just try to guess it, which is probably like way easier, At the same time, this is the birth of algebraic topology. So algebraic topology, well, there's a couple different sources, but like one is this thing I'm talking about, finding closed forms which are not exact. That reveals the existence of non-trivial topology in the space. That's like one. This is the so-called de Rham cohomology, which is maybe about as old as cars, give or take. I mean, I think de Rham cohomology is from the early 20th century, maybe. Other aspects of algebraic topology are older, like Euler's results about calculating triangulations of spaces and calculating what are called, oh man, I can't remember the name of that stupid number. But we'll talk about it next week. So that's the next thing, is we're actually going to take a brief digression away. So we're not, next class, not the whole week, but the first class, Tuesday, I am going to show you classical geometric homology theory. Which we're not even going to, there's no calculus in anything we're doing next time. It's pure algebra and geometry. So I think you guys will enjoy it. But anyway, shut up.